All right, so here I've got some just kind of basic trig problems that we can look at. So the first one says the terminal side of an angle theta is given by the equation 7x minus 5y equals 0, where x is less than or equal to 0. And we're asked to evaluate all 6 trig functions for theta. So sine theta, cosine theta, tangent theta, all of that. Okay. As usual, and I think that this is especially true in trig, making a picture is helpful. Anything that is sort of geometric or geometry adjacent, making a picture is always going to be helpful. Okay, so, and the picture here that I want to look at is, I just want to get an idea in my head of what this angle theta even looks like so I can start moving towards this. So we have this equation 7x minus 5y equals 0. And we want to sort of, at least what I want to do, the way I think about this, I want to see what this angle looks like just because it sort of helps me. What you could do in order to find, to draw this angle is, if it's not obvious to you, this goes through the origin. If you plug in x and y, then you get the equality. So it's going to go through the origin, which is good. It would be a really strange question if it wasn't going through the origin. But we need another point then to kind of create the line. You could choose something. So remember that x is going to be less than or equal to 0. So you could choose, like, let x be -1. And then solve this out, but you're going to end up with some kind of fraction that you're working with, which is not a problem. It's just that I don't like working with fractions. You can, like what I just said works. You can plug in any number. You can plug in x equals -1 if you want, solve it for the corresponding y. You can plot that point on here and then solve everything out the exact same way as I'm about to. It's just that for me, I'm lazy. I don't really like working with fractions very much. So I think what I'll do instead is I will solve this thing for y, just because that helps me to get an idea in my head for what this looks like and what might be a good number to plug in that avoids fractions. So 5y equals 7x, which means then that y is equal to 7/5 x. And maybe you already kind of saw what the clever numbers are that you can put in, which is essentially just kind of plugging in the reverses, but this makes it a little bit more obvious. What number can we plug into y equals 7/5 x in order to make, like, where x is an integer that also forces y to be an integer? So if you don't see it, maybe pause for just half a second and think about it. What would be a really smart value to plug in for x? I think if x equals 5, then when we plug in x equals 5 here, the 5's just cancel. So y equals 7. Right, I guess I should have plugged in, how about -5 actually, since x is less than or equal to 0. So if I plug in -5, then we still get integers, it's just now they're both -2. Okay, so what this is saying is that this angle theta goes through the point -5, -7. The scale isn't all that important. We're just trying to get like a generic idea of what this looks like. So here's our angle theta, and theta always lifts off of the positive x-axis and ends at whatever line it is. So technically theta is this whole angle, but the way to kind of think about this is to drop a perpendicular from this point to the x-axis so that we can make a triangle. And then, like, if you're thinking about reference angles, this is the reference angle in here. Call it theta prime if you want. But the upshot here is that this kind of tells us we have this triangle now where this side length is -5, and we need to be careful about the negatives, even though they're side lengths, since they're on the Cartesian plane, they can be negative. So those will both be negative, and we need to solve for the hypotenuse. So the hypotenuse is going to be the square root of 25 plus 49. So that's just the Pythagorean theorem. 25 plus 49 is 69, 74. Let's see, does that have anything? Half of 74 is 37. So no, I don't think that can be simplified at all. So here's our triangle with all of the side lengths listed out. So now all we need to do is just list out what is sine theta, cosine theta. So two different ways that you may have learned sine theta at this point. So sine theta is y over r. So negative 7 over root 74. And remember, you need to rationalize this. Anytime you have a root in the denominator, you need to rationalize it, which just means multiplying the numerator and denominator by whatever, at least if it's a square root, by multiplying it by whatever is in the denominator. So if I multiply top and bottom by root 74, then I get that this is negative 7 root 74 over 74. So this is y over r, but this is also, if you think about it internally, thinking about it like SOHCAHTOA, this is opposite over hypotenuse. So either way, you get the same thing. Cosine theta is adjacent over hypotenuse, or x over r, so negative 5 over root 74, and then after we rationalize it, negative 5 root 74 over 74. And don't just take my word for that. If you can't see how it rationalizes in this way, go through the same steps and make sure that you get the same thing. It's possible I made a mistake, but I don't think so. Alright, tangent theta is y over x, or opposite over adjacent. So negative 7 over negative 5, which is positive. 7/5. Alright, and then the reciprocals, so cosecant of theta would be negative root 74 over 7. I'm just taking this and flipping it on its head. Secant theta is negative root 74 over 5, and then cotangent theta is 5/7. And that's it. All right, so the next question says, given that tangent theta equals 3 over 4, and theta is in quadrant 3, I guess we're working with another angle that's in quadrant 3, evaluate the other 5 trig functions for theta. All right, so once again, just a really quick sketch might be helpful. Here's my plane. I know that theta is in quadrant 3, so it's going to be over here somewhere, the bottom left. And I know that tangent theta is equal to 3 over 4, but tangent theta, in terms of kind of the coordinates on the graph, is equal to y over x, or in terms of relationally within a triangle, it's opposite over adjacent. So the y-coordinate here has a length of 3, the x-coordinate here has a length of 4, but remember, this is in quadrant 3. So both x and y are negative over here. So it must be the case that y is negative 3, x is negative 4. And that makes a lot of sense then, because that forces tangent to be positive since it's negative over negative. So here's our theta. I didn't actually mean to put both of these in quadrant 3, but theta is this angle right here. And if it's helpful, make your right triangle again. So this side right here is a length of negative 3. The adjacent side is a length of negative 4, and you can use the Pythagorean theorem to solve out the hypotenuse. It's going to be 5. It's a 3, 4, 5 triangle. And then once you've done this, everything else just kind of falls in place, just like we did up here. So sine theta is opposite over hypotenuse, so negative 3/5. Cosine theta is adjacent over hypotenuse, negative 4/5. Cosecant theta is negative 5/3. Secant theta, negative 5/4. And cotangent theta, we didn't even have to do any work. Cotangent is just given to us because of tangent, is 4/3. So that's the solution set there. could box these off too. Somehow it seems more like final if you actually box it off. It's like confident, like, yep, here's the answer, I know it. And sometimes you box it off and it's wrong, and you feel a little tinge of embarrassment. We've all been there. All right, so next we're given a triangle and we're asked to solve the triangle. And when you're asked to solve a triangle, what it means is find all of the side lengths and all of the angles. So which is the easiest one to do here? And if you're kind of like working along with me here, I would suggest just take a hot second, pause the video, try to work this all out on your own. Figure out what the hypotenuse is, figure out what this, the bottom leg is, figure out the angles, and then come back. So for me, looking at this, the easiest thing to do, I'll call this angle down here like alpha. The easiest thing to find is alpha, because that just comes from the internal sum of angles. So it'd be essentially, there's a few ways to think about it, but really explicitly 180 is equal to 90 plus 50 plus alpha. So we just solved this for alpha. 90 plus 50 is 140, so alpha is 40 degrees. And then from here, solving for the other pieces, you can either choose to use alpha, or you can choose to use the 50-degree angle. I'll use the 50-degree angle just for the reason that sometimes when the triangle is oriented this way, I think it can be kind of easier if the angle that you're looking at is sort of in the bottom left or the bottom right. If you're looking at an angle that is in the top, sometimes it might be a little bit confusing because you have to make sure your orientation of what is the opposite side, what is the adjacent side, all of that is correct. So I'll use this 50-degree angle, and first I'll solve for the hypotenuse. So what that means is I have an angle, I have a side that is adjacent to the angle, and I'm looking for the hypotenuse. So which function relates the adjacent side and the hypotenuse? That's cosine. So what this is saying is that the cosine of 50 degrees is equal to the adjacent side over the hypotenuse. So solving this for the hypotenuse, it's 7 over the cosine of 50 degrees, which comes out to, if you're typing this into your calculator and you're typing it in as degrees, make sure that you are in degree mode and not in radians, which is the easiest mistake to make in trig. Everybody makes it, at least once, every single buddy. Okay, so the hypotenuse must be 10.8901 units, whatever it is, feet, centimeters, meters, I don't know, bananas. From here, we just need to solve for this last leg, which there are two ways at this point, two viable ways to do it. One, you can do the Pythagorean theorem. Because this is a right triangle, we have two of the legs, so the Pythagorean theorem gives you the final leg. Or you can also use a trig identity, which is what I will do. Again, just for the sake of kind of getting used to using an angle that's not in the bottom left or bottom right. And even with this, there are two viable ways of doing this, because we have two different side lengths that we can use. So I could either use the hypotenuse along with this opposite side, so that would be sine of 50 degrees is equal to this bottom leg divided by 10.8901. I'd rather stick with the whole number, the 7. So I have at my disposal, I have the adjacent side. I'm searching for the opposite side. What relates opposite and adjacent sides is tangent. So I have that tangent of 50 degrees is equal to opposite over adjacent, which is 7. So then the opposite side must be 7 times the tangent of 50, and that is 8.3423. So So I like to carry all of my rounding, I like to carry it all out to 4 digits because I think that that maintains the most precision and still allows me to be lazy. Alright, and I've got one last problem here that we'll look at. So we're given this sort of triangle. It's actually kind of two triangles, but there's this larger triangle, there's the smaller triangle within it. We have the angle measures, and then this 110 is specifically just this distance right here. And we want to find x. Well, if you just kind of look at this, we don't quite have enough information. Well, we do, but we don't have enough information to solve this like just kind of straight away, like how we did this one, where we were able to just immediately start saying, oh, tangent or sine or whatever. This one we have to do a little bit extra legwork. And what would be especially helpful is, like, I'm just kind of thinking about this. So I have these two angles. I'm looking for the side that is opposite of those angles, and I'm given partially the side that is adjacent to those angles. So what might be the trig function that I want to use, the one that relates opposite and adjacent? Cotangent or tangent. So tangent is opposite over adjacent. I suppose you probably could use cotangent on this one, and it might actually make things a little simpler. But in any case, they'll both get you there. So the first thing that I'll do is I'm going to give this side a name. I'll call it y. I don't know. You can name it whatever you want. It doesn't matter. And once I have that, now I can write expressions for the tangent of these angles. So for this smaller angle, the 23-degree angle, I would have that the tangent of 23 degrees is equal to the opposite side, which is x, and this is a right angle, by the way. So it's x over the adjacent side. But the adjacent side is this full bottom piece. It's not just 110. It's 110 plus y. So the tangent of 23 degrees is equal to x over 110 plus y. The tangent of 47 degrees in this sort of smaller triangle is going to be opposite, so x over the adjacent, and this time the adjacent side is just y. And now we have two equations with two unknowns, and that is solvable. So how do I solve these? Well, I want to solve for x. That's specifically what I've been asked to find. So I'm not particularly worried about y. So my thought is, for both of these equations, I will solve both of them for y and then set them equal to each other. So this second one is the easier one to solve for y, because y is equal to x over the tangent of 47. So y and the tangent of 47 just kind of swap places. This other one, there's a little bit of extra work that needs to be done, just because there's this 110 being added on to y. But it's a similar idea, and you might want to convince yourself of this, but it should be the case that y is equal to x over the tangent of 23 degrees minus 110. Yeah. And now I have, is it not focused? There it is. Okay. Now I have these two equations, both of them set equal to the same variable y, which means these two equations are equal to each other. So I'll set up my new equation, x over tangent of 23 degrees minus 110 equals x over the tangent of 47 degrees. And now I've got an equation with just one variable, x, which is what I want to find. So I just need to solve this thing for x. And this goes back to college algebra. We did these sorts of things. Go on. We did these sorts of things a lot in college algebra. So the general procedure for something like this is move everything with the variable, anything that involves a variable, move that to one side, move everything else to the other side, and then you'll have to factor out the variable. So my first move is that I would say this is the same as x over the tangent of 23 degrees, and then I'm moving this piece over to the left, so minus x over the tangent of 47 degrees. And I'm doing like a couple of steps in one. So if this is like too fast for you, just slow down. Do it one step at a time. So then this 110 gets added to both sides, so it gets moved over. So I'm right here, and now that everything on this left-hand side involves an x term, I can factor that out. So it would become like x times 1 over the tangent of 23 degrees. And notice that I'm not calculating out these tangent yet. One, because you would actually have to write more. Neither of these are going to evaluate well. They're going to both be decimals. So that's why I avoid that. You're going to have to write a lot more, but maybe moreover, the more important reason is because you always, just as a general rule, you want to save as much as possible, save the rounding to the very end. Like once you have the actual like calculation, that's when you round. If you can help it, avoid rounding before then. So this is the most precise expression. Tangent of 23 degrees is precise. All right. So the very last thing that we would need to do is essentially we need to calculate this all out and divide it over. So x equals, I'm gonna write this kind of funny, but just to give you an idea of what I'm going to be doing, it's going to be 110 divided by all of this, because this is just some number. You can divide it over. Minus 1 over tangent of 47 degrees. So 110 divided by all of this business, and then now I plug it into the calculator. And by the way that I do this in the calculator is because I don't trust order of operations in any calculator ever. I would do something like this: 1 divided by tangent of 23, and then from that I will subtract this 1 divided by tangent of 47, but I'm going to put the whole thing in parentheses. 1 divided by tangent of 47 degrees. So this gives me this 1.4233 figure is the denominator here. So I need to do 110 divided by that. And again, rather than like rounding this, I'm literally just going to do 110 divided by this second answer. And my calculator can just do all of the rounding, carry this, whatever this number is, however many digits it wants to. And it gives me 77 point all of this. And then now that I'm at the very last step, I have the final calculation. Now I'll round it. So x is 77.2832 units, whatever the units are. I didn't put units on there. But yeah, that's the answer. Okay, let me know what questions you have.